Right, so let's look at order statistics today. Have you heard about the term? Have you heard the term order statistics earlier? Well, when you see the term order, you can guess what it is. If you arrange things in order, right, that is ordering, maybe ranking, right? So similar to that, random variables also you can order them, okay? Now, what does that mean? If you think about functions of random variables, okay, sometimes you will be interested about, but depending on the magnitude of these random variables, their values, sometimes you are interested about the highest value or the smallest value, okay, maybe in between values, okay, the midpoints and so on. Now, if you want to find the highest value or the smallest value, you know the terms we use, minimum and the maximum. Okay, sometimes it is important to know the behavior of this minimum and the maximum. Sometimes in betweens, like the percentiles, quartiles, okay, the exact midpoint and things like that. Now, if you want to find these rankings, you have to order your data set. Okay, now think about a practical situation. Now think about you have a sample of students and their exam scores. You want to find who has the highest exam score, who got the highest marks. So that will be the maximum of the exam scores. Okay, so you can find the maximum value. And if you want to find who got the lowest grade, that will be the minimum exam score. And if you want to find what is the midpoint of the exam scores, that means at that score, there will be 50% who received less than that mark and 50% who received more than that mark. That is the exact midpoint. And if you want to find that, you have to order your exam scores from minimum to the maximum. Okay. Now, if you think about another situation, now think about a race. Okay. If it is say 100 meters, the first person, okay, the first one to finish it will record the lowest time, right? So that is the minimum time. And the second place will be the next minimum. Third will be the next one. Okay, so likewise, you look at the time in descending order in that case. Okay, you in the first example, you arrange the exam scores in ascending order, so you can find the highest score. And if you think about a race, if you arrange the time values from descending order, that is the smallest to the largest, or minimum to the maximum, that will give you the ranking first, second, and third places. So likewise, in some situations, we are interested about finding the minimum, maximum, and then any other the placements. So you need to order your data. Okay. So we call that the order statistics. So if you order your random variable, so let's say so you do that according to the magnitude. We call them order statistics. Okay, now think about your random sample. Let's denote in the usual notation. Your random sample is x1, x2 up to xn. Okay, now if you arrange this in ascending order, right? If you arrange them in ascending order, now these values, we do not know, they may be jumbled up. So if you put the smallest one, let's say x1. Now remember x1 here, x subscript 1 and x within parentheses 1, they are not the same. Okay, this x parentheses 1 means the smallest number. Okay, so that will be less than or equal to the next one, and comes the next highest one, and so on. You go up to the largest one. So x parentheses n is the maximum. So this is the minimum, and here's the maximum. And usually we denote them as y1, y2 up to yn. Okay. So remember these notations, x1 and x parenthesis 1, they are different. Okay. They are different. That means the value. Okay. This is only the notation of the number. But when you arrange them in order, x parenthesis 1 means the smallest number. X2 is the second one, and so on. Okay, so you go up to the maximum. And we denote them using y1, y2 up to yn. Okay, so you can say 1, which is y1. This is the smallest observation. Okay, and you can say this is the minimum of xi, where I goes from 1 to n. So this is another notation to write the minimum min of xi, where I can be 1 up to n. Okay. Then what is y2? Okay, so if you think about y2, y2 is that is the second smallest observation. Okay, so likewise, you go up to yn, which is the maximum. This is the largest. We call it the maximum. So you can write max of xi, I goes from 1 to n. Okay, so all these are the notations that you can use with the order statistics. Okay, now say for example, look at this small example of size 5. Okay, you have a random sample of size 5. X1 is 32, X2 is 45, X3 is 23, X4 is 12, let's say X5 is 40. Okay, so shall we order this data set and tell me what is X1, what is X2, X3, X4, and X5. Tell me these order statistics. So this will be Y1, Y2, Y3, Y4, and Y5. Okay, so what is the smallest? You can clearly see that it is the 12. Yes, it is the 12, 23, 32, 40, and 45. Okay, so you can easily figure that out. So this is 12, 23, 32, 40, and 45. Okay, now you can see x1 and x parenthesis 1. They are not the same. Okay, so this is your ordered data set. So x1, x2, this first set, x1, x2 up to x5, that is your random sample. After you order it, y1 up to y5, that is your order statistics. Okay. Now this x1 up to x5, the original data, they are independent. Okay, so remember this carefully. These xi's, the original data set, they are independent. Okay. But when you order them, are they independent? When you order them, will they be independent? No, they are not going to be independent. Why? Because 12 becomes smaller one because it is less than 23. So depending on each of these values, the positions are designed. Therefore, after you order your data, they are no longer going to be independent because, okay, so you got the first place because it is smaller than the others. Okay, you got the second place because it is greater than the first one, but smaller than the rest. So they all are depending on the values of each other. Therefore, although the original data set, the star, the original random sample, it is independent, but after you order them, they become dependent. Okay, so they become a dependent sample, right? So we'll note it down quickly. Okay, so this is important. You have to keep this in mind very thoroughly. Xi's are independent. But yi's are not. Okay, not independent. And the other thing is we can find the distribution of these yi's. Okay, so you can find the distribution of these order statistics. And this is what we are going to look at is in this section, right? It is possible to find the, we call them the sampling distribution. The sampling distributions of yi's. Okay, so that means you can find what is the distribution of the minimum. What is the distribution now? That means you can be able, you can find the PDF and the CDF. Okay, you can find the probability density function, the cumulative density functions, and so on. And if you know the PDF, CDFs, you can find probabilities. You can find the averages, the variance. You can find all these calculations when you know the PDF and the CDF, right? So for the minimum, you can find the PDF. You can the maximum. You can find the PDF, the CDF, and everything. If you want to find the PDF of Y3, you can find it. If you want to find the joint PDF of Y1 and Y5, that is the minimum and the maximum, that is also possible. And if you want to find the distribution or the PDF of Y1, Y2, and Y3, the joint distribution of first three smallest order statistics, that is also possible. Okay, so that is what we are going to look at in this course, especially the minimum and the maximum. We are not going to pay more attention on the other in between order statistics here, but it is possible. Okay, right. So in this case, we are going to specifically look at the PDF and CDF of min and max. Now, in addition to the examples I mentioned earlier, if you think about other practical situations where you use the PDF and the CDF of min and max, we'll do a few examples. But in addition to that, especially in, if you think about reliability analysis, survival analysis, you need the distribution of minimum and the maximum, right? Say, for example, if you have a system of components attached in series or in parallel, you know how these electronic components are, attached. Sometimes they are in series, sometimes in parallel, sometimes combinations of series and parallel. And, depending on the way they are attached, the lifetime is going to be different. If you have three components in series, when the first one fails, the whole system fails, right? Although the others are working. If you have a series system, when the first component fails, the whole system will die. But if it is a parallel system, in all three components are in parallel, when the first one goes away, still the others two are working, so the system will work. When the second goes away, still there's another path to go, so the system will work. And when the last one goes away, the system will fail. That is the maximum. So the maximum lifetime of the three components will be the lifetime of the whole system. So those type of probabilities, when you need such analysis with components, their reliabilities, production, that is where these PDFs and CDFs are very important in practice. Okay. So here's the definition of the minimum and the maximum. Okay. Now suppose you have x1 up to xn, the independent and identically distributed random variables, right? You have independent and identically distributed random variables. That means the IID, right? I write it again, independent and identically distributed. And the sample size is n. And the CDF of this original IID random variable is capital Fx, and their PDFs are Fx. So all of them, now they are independent, they are identically distributed. So x1, x2, xn, all of them have the same probability density function Fx. Okay. If it is discrete, it will be the PMF Px. And the CDF, the capital Fx. And let's order them together. Now, after you order these samples, you get y1 up to yn. That is your order statistics. Okay, then if you define the maximum of this data set, that is yn, Okay, this is how you write the CDF of yn, the maximum. Okay, for the maximum. So you can see the notation Fyn. Now our variable is y, not x. Okay, so that will be 1 minus capital Fxy. Now this Fx is the original Fx. Okay, this Fx is the original Fx, but evaluated at y. Okay, and whole thing to the power n. I'll show you how to derive these statements. Okay, but now, for now, look at these equations. And the PDF of the maximum, you get the first derivative of this with respect to x, and you'll end up with n fxy to power n minus x. And the chain rule, go inside fx. The first derivative of capital Fx is the PDF simple fxy. Okay, in the similar manner, if you think about the minimum, now we have y1. So fy1y, that will be 1 minus fxy to power n. And if you take the first derivative of this one, you get the PDF, simple fy1y. Okay, so these are the CDFs and the PDFs of the minimum and the maximum. Okay, now these, I'll show you how to derive them. So if you you should know these equations. You don't have to memorize them, but you can derive them whenever they are needed, right? So therefore, if you know the CDF, that's enough, because you can get the first derivative and get the PDF. And actually remember in the PDF, it's easy. Okay, it's not complicated. Okay, you can easily remember that. Okay. Right, so let's try to get the proof. Okay, so let's start with the maximum. Okay, so let's consider the maximum. So yn is the max, or you can say the nth order statistic. We are using the distribution function method. Okay, we are using the distribution function method. Right. So that means we start with capital Fyny. Right. That is the CDF. So let's start with the definition of the CDF. What is the definition? Probability yn is less than or equal to y. So this is just the definition of the CDF, right? Here's our random variable yn, and it denotes the values are denoted as y. So yn less than or equal to any y. So that is our the definition of the PDF. Okay, but we know yn is the maximum. So you can write yn as the max of xi, where I is from 1 to n. The max xi less than or equal to y. Okay. So the maximum of xi is less than or equal to y. What does that mean? If the maximum is less than y, what about the other values? If the largest number is less than a certain value, so what about the rest of the values of xi? If the largest is less than, then the others should also be less than, right? So why? Because now let's think about I'll give you a small example just to explain this one. Now think about this data set, 2, 7, 8, 9, 10. Okay. Now this is our data set. It is in order. Here's our max. Now if our y is 20, our y is 20, and you can see that 10 is less than or equal to 20. When 10 is less than or equal to 20, other values are, well, they are less than the maximum, because 10 is the max. All the others are less than that. So when the max is less than 20, obviously the rest will be also less than 20. Right? It is very clear. Therefore, we can write this as the maximum less than or equal to y means x1 is also less than or equal to y. x2 is also less than or equal to y, all the way up to the xn. Okay, why? Because now think these are xi's. Xi's are independent. Okay, they are independent. Therefore, and now I'll write it in the in-between line also, so that will be easy to understand for you. Okay, let me write the in-between number. So xi less than or equal to y means x1, x2 up to xn, all of them are less than or equal to y jointly. But xi's are independent, right? Therefore, you can say that the joint density is the product of the marginals. So you can write it like this. Now, these are not the order statistics, okay? These are just xi's, okay? And they are independent because max of xi, right? So that means all the others are less than or equal to y. Is this clear to all of you how we got this argument? The max of xi less than or equal to y means the rest, okay? The rest of the values, obviously they are also less than or equal to y. And you can write this as the product because xi are IID. They are independent. So the joint density becomes the product of the marginal. Now, if you look at these statements, what is this? Pxi less than or equal to y means this is the Cdf of y, okay, at x1. And this is again the Cdf of y. Okay, it doesn't matter whether it is x1 or x2, right? They are identically distributed. Therefore, in all these expressions, that denotes the Cdf of x. So you have fxy how many times? N times. So you get fxy to the power n. You multiply fxy n times. Okay. So you end up with the Cdf of the maximum to be fxy to the power n, right? So this one. Oh, this is wrong, right? So it should be, okay, just fxy to the power n, okay? Right. And then you got the PDF of the maximum. How do you find that? Fy ny is the first derivative of capital Fin y, right? So you get d over dy f x y, and now you have to look at these substitutes, okay? The subscript, the yn and x, okay? This is the Cdf of x's. This is the Cdf of the maximum. So you have to be very careful with this subscript, okay? Right. So how do you get the first derivative? Right. So this is with respect to y, right? This y. Right. So here's the function of y. So you get n times fxy to power n minus 1. This is the usual way you get the derivative. And then you go inside the chain rule. The derivative of fxy will be simple fxy. Okay. So that is the, see, this is how you get the PDF of the maximum. So Fy n y is n capital Fxy to power n minus y multiplied by the Cdf of Fx. Okay, so you know the density functions of x, the random variable for the original random variable, the sample of random variables, that Fx and capital Fx. When you know them, you can easily find the Cdf and the PDF of the maximum. Okay, so this is how you derive it. If you know this idea, right, the maximum is less than or equal to y, that because we start with the definition of the Cdf, you can easily derive these two expressions. Okay. Now, similarly, let's do the let's derive the PDF and the Cdf of the minimum. Right. So now let's consider the minimum. Okay, that is y1. So that is this, the smallest, or you can say the first order statistic. Okay. Again, we are applying the distribution function method. Okay, so let's try to find Fy1 y now. Okay, y1, Fy1 is the minimum. Again, let's apply the definition of the CDF. So that will be Py1 less than or equal to y. Again, this is the minimum of xi, I from 1 to n, less than or equal to y. Okay. Now, in this case, now let's go back to that small example. Okay. So you see that 2, 7, 8, 9, and 10. Again, let's say our y is 20. Okay. Now, when you say 2 is less than or equal to 20, we cannot make any, any statement about the rest, right? Although 7, 8, 9, 10 are less than 20. Okay. Now let's take another, let's say, okay, I'll use another example. Let's say, okay, here's our same data set. Let's say 2, 7, 8, 9, and 10. Now, if you use a number, let's say 9, okay, it's when you say 2 less than or equal to 9, 7 is less than or equal to 9, 8 less than or equal to 9, but 9 and 10, you can't say they are less than or equal to 9. Okay, 9 is okay, equal sign is there, but 10 less than or equal to 9, that's not true. Okay, therefore, you cannot guarantee when the smallest is less than or equal to a certain number, you can't guarantee what will happen to the rest of the numbers. Okay, they can be less than or sometimes they will exceed. So this inequality, we cannot guarantee that it will be true for everything. Therefore, we are going to look at the other side. Okay, so what I'm going to do is I'm going to take 1 minus of this. If I take 1 minus, what will happen? You know that the sign will change. Right? If you take 1 minus, that is the opposite. Okay, now you have xi greater than y. Now we have this expression that the minimum is greater than some number. Okay, say for example, the minimum is 2, let's say 0. Right, so the minimum is greater than 0. So 2 is greater than 0. That is correct. If the minimum is greater than 0, obviously the rest should be greater than that. Okay, so that is clear. When the minimum is greater than some number, that means the others are automatically going to be greater than that. Now that is true for all the values. Therefore, we can proceed with this 1 minus p expression. Okay, so we can write this is same as the probability x1, x2, all the way up to xn. All of them will be greater than that y. Is this clear to all of you? How we generated this argument? When you say less than or equal to y, we cannot guarantee that with the minimum. But if you make it greater than some number, then we can guarantee that all the other values are also greater than y because x1 is the minimum. Okay, is this clear to all of you? Right? And when we say, again with the IID, the independent distributions, you can write this as P x1 greater than y times x2 greater than y all the way up to probability xn greater than y. Okay, we have 1 minus at the outside. Okay, we have 1 minus outside. And again, what is this p x1 greater than y? If you want to write it in the CDF, this is same as 1 minus p x1 less than y, right? And then you have p x2 greater than y means 1 minus p x2 less than y. And so on, you can write all the way up to 1 minus p xn less than y. Okay. And what is this? P x1 less than y means 1 minus f xy. They are identical, right? And then again, you have 1 f xy. So likewise, up to the nth one, you have 1 minus f xy. So that means you have 1 minus f xy how many times? N times. So you can write 1 minus f xy n times. Okay, better to write it like this. Okay. 1 minus fxy n times, and you have 1 minus outside. Okay, and you can see that is the, see, this is the CDF of the minimum. Okay, so here you have the CDF of the minimum. And then to find the PDF, what do? You get the first derivative with respect to y. Right? Can you find it? So that will be d over dy 1 minus fxy to power, sorry, n is inside, right? Okay, so when you take the first derivative, 1 is a constant, but you have negative sign. Right? 1 is 0, the derivative of 1 is 0. And then you have this negative sign, and the derivative of 1 minus fxy to power n will be n times 1 minus fxy to power n minus 1. Right? And then you have the chain rule inside this. Again, you take the derivative of 1 minus fxy, y is 0, and again you have the negative sign, this negative sign, and the derivative of fx is simple fxy. So this negative and this negative cancels out. And at the end, you will end up with n times 1 minus fxy to the power n minus 1 times fxy. So that is the PDF of the minimum. Okay, so those are the 4 equations you need in this course: the CDF and the PDF of the minimum and the maximum. Okay, now is it clear to all of you how to derive these distributions, the argument? Okay, and the other thing is xi's are independent, but yi's are not independent. Okay, yi's are not independent. Right. So here's the summary of so it should be, here's the summary of the CDF and the PDF of the minimum and the maximum. Okay, so this will be like the summary. This is what you have to remember. Okay. Now, keeping those in our head, let's try to do an example, right? So here's the first example. It's based on the uniform distribution. Suppose that the time in minutes you need to wait for a bus is uniformly distributed on the interval 0 to 15. Let's say these are minutes. The waiting time is uniformly distributed within the interval 0 to 15. So when you see this uniform distribution, okay, now you should get the idea in your head. Uniform distribution, what is the CDF, what is the PDF? Okay. If you take a bus 5 times, what is the probability that your longest waiting time is less than 10 minutes? Okay. Now it is not the waiting time is less than 10 minutes. It is the longest waiting time. So you should be very careful. The waiting time is uniform, but you have to find the longest waiting time. The longest waiting time, what is it? This is the max, right? So you have the distribution of the waiting times. The waiting time is X. X is uniform within the interval 0 to 15. But we are interested in finding the probability of the longest waiting time. Okay. So that is Y. So first you have to derive the distribution of the longest waiting time, which is the maximum of this X's. And using that maximum, you have to find the probability that it is less than Y. Okay. So remember, when you have to find the longest waiting time less than 10, that is not that the probability X is less than 10. No, it is the probability that the longest waiting time, that is the maximum, is less than 10. Okay. So this is what we want to find. So if you want to find the probability of yn less than 10, you should know the PDF of yn. Then only you can find this probability by integrating it from 0 to 10. Okay, so the first step, you have to find the distribution of yn. In order to find the distribution of yn, the maximum, you need the CDF of the x. Okay, so let's start with finding the PDF and the CDF of x. Okay, is this clear to all of you? The waiting time is x, but our probability that we have to calculate is the longest waiting time. So that is the maximum. So you have to derive the PDF of the max first. Okay. Now, when you see that the x is the uniformly distributed, okay, remember when you have uniform distribution, when x is uniform within the interval alpha and beta, what is the PDF? That will be the 1 divided by the length of the interval, which is beta minus alpha. And x will be in between alpha and beta, 0 otherwise. This is the uniform distribution. So in our case, alpha is 0. Beta is 10, so 10 minus 0 is 10, 15. So 15 minus 0 is 15. So you have the CDF of the PDF of x is 1 over 15. 1 over 15 minus 0, which is 15. So X is in between 0 and 15. So this is the PDF. Then how do you find the CDF? You have to integrate fx from the lower limit up to any x. Right? So if you integrate, right? So if you integrate 1 over 15 from 0 to any x, what do you get? 1 over 15, x from 0 to x, that will be x over 15. So that is how you got this CDF. Okay, simply integrate from lower limit up to any x. So you can write the PDF and the CDF of the x, that is the waiting time. Okay, so that is our first step. Sometimes this the PDF or the CDF will be given to you. Okay, then no problem, you can use it in your derivation of the maximum. But in this case, it is only given that it is uniform from 0 to 15. So you should be able to derive the simple fx and capital Fx. Then use it to find the longest waiting time. Okay, so you need the PDF of the maximum, and we already derived it. Here's the PDF of the maximum, right? So use it here. We know fx, we know simple fx. So just apply it into this formula. N is 5. Why? It says if you take the bus 5 times, so you are doing it 5 times. So that is your random sample. Okay, it's 5 times. So N is 5. So you have N5, fxy is y over 15. Now remember, see, you have fx at y, right? What is your capital Fx? This one at y. So replace x with y. So you have y over 15 to the power n minus 1 is 5 minus 1, 4 times fxy. What is fxy? Yes, fx. This is capital Fx, right? So when you have fxy, instead of x, you put y. But in the expression, it is just 1 over 15. So you multiply it by 1 over 15. So you'll end up with this expression. So here's the PDF of the maximum. Now use this to find the probability. What is the probability you need? The maximum waiting time is less than 10. So you integrate your newly found fy5. Okay, so this one is the maximum. So here's it. You integrate it from 0 to 10 because it should be less than 10, right? So the lower limit is 0 because it is from 0 to 15, right? See, so integrate from 0 to 10, and this will be the probability that the longest waiting time is less than 10. Okay. So is this okay? Any questions? Anything unclear? So remember, waiting time is x. The longest waiting time, that is the maximum. So you have to derive it, right? But if you want to find the smallest waiting time? If you want to find the smallest waiting time is greater than 5, how do you find it? Say, for example, you want to find smallest waiting time. Smallest waiting time is greater than 5. How do you find it? You have to find the distribution of y1. Okay, so how do you find the distribution of y1? Here is it. It is, you know fx, you know simple fx, right? You can simply apply this number, okay? And after you find y1, you integrate it from where to where? Greater than 5, 5 up to 15. After you find the PDF of y1, you do this. Okay, so you can end up with the probability that the smallest waiting time is greater than 5. Okay. So when you understand the method, it's nothing hard, right? You know the distribution of minimum and the maximum. Okay, you can use it. Now here's another. What is the expected longest waiting time? The expected longest waiting time. What does that mean? This is the mean, right? Expected value is the mean. Mean of yn, or in our case, y5. So how do you find it? Okay, how do you find the expectation? That will be x times fx dx. So in our case, it is y. So you multiply the density function of the maximum by y, right? and you can find the so here's 5y to the 4, 15 to 5. You have the PDF of the maximum, multiply it by y, and then integrate over the support. Support is from 0 to 15. And you can get the average longest waiting time. So what is this? This is the average longest waiting time. If you wait 5 times for the bus on average, what will be the longest waiting time? You can find it. Okay. And if you want to find the variance, you can do that. You find EY5 to power 2 and then use the computational formula for variance. And you can find the variance of the longest waiting time also. Okay. Right, is this clear to all of you? How you use the maximum, the distribution of the maximum, right? So here's another example. Let's look at this also. Suppose that the length of time x that takes a worker to complete a certain task has this given PDF. Okay, where theta is a positive constant. X is greater than theta. Okay, so e to the power negative x minus theta, x greater than theta. So this is the PDF of x. You have to find the PDF of the minimum time needed to complete the task. Okay, you have to find the PDF of the minimum time needed to complete the task. And then you have to find the expected minimum time using it. Okay. Now, how do you do this one? Now the fx is given, but you need capital Fx. Okay, because in the equation of the PDF of the minimum and the maximum, both simple Fx and capital Fx are there. Therefore, when simple Fx is given, okay, you have to find capital Fx. This is given. This you have to find, right? So let's find it first. You need the Cdf of x. So how do you find the Cdf? You have to integrate from the lower bound up to any x. So it will be from theta up to x, the PDF. So when you do that, you will end up with 1 minus e to the negative x minus theta. So this is the Cdf of x. Now you use it in the equation of the minimum. Here's the equation of the minimum. What is it? N times this one, n times 1 minus fx to n minus 1 times fxy. Right? So you have 1 minus and fx is again 1 minus. So it goes here to power n minus 1 and then you multiply it with fx. Now in this case, the value of n is not given. So your answer will be in terms of n. Okay. And the sample size is not given. So you leave the answer in terms of n. Right. So you find the PDF of the minimum. Okay. And using this, you can find the expected value. Right. So, okay. So that is part B. The expected value of y1 is, right, you get n e to the multiply by y n times e to the negative x minus theta to power n dy. You have to integrate it from where to where? It's from theta up to infinity. Okay, so y times the PDF of y1. That will give you the expected value of y1. And if you know the value of n, you can substitute it here and calculate it. Right. So here are some examples for the use of minimum and the maximum. Okay. So usually in examinations, there will be a part for you to derive the min and the maximum. Okay, so you have these equations with you and use it in the calculation. Okay, right. Okay, so that's about the order statistics. As I mentioned, we only focus on minimum and the maximum in this course. But if you are interested on how to find the orders, how to find the PDF and the CDF of the in-between numbers, say y2, y3, or y4, okay, likewise, you can refer them. There is a method called the heuristic method. Okay, Okay, using that, you can very easily derive the distributions of the other values. Okay, in addition to the smallest and the minimum and the maximum, the in-between distributions we can very easily derive it, and also the joint densities. Okay, there's a method called heuristic method. You can search it. Okay, you'll see how you can derive these distributions. Okay, so that is something extra if you are interested about. Okay, you can refer it. Right. Okay. Now, can you remember we talked about the sampling distribution of sample mean and sample proportion in that introduction last week? Okay, I explained you about the sampling distribution, the difference between the population distribution, the data distribution of the sampling distribution. So now we are going to look at the sampling distribution of sample mean, sample proportion, and sample variance. Okay. Now this is a little bit different. Now this order statistic part is that's done. Okay, so there's no connection in between order statistics and the sampling distribution. This is the next section of the chapter. Okay, so it is about the sampling distributions. Okay, now suppose that the PDF of some population where you draw a sample of size n, they have the PDF of X. Okay. Now, when you know the density function of a sample of random variables, you should be able to figure out the distribution of the sample mean, not the value of the sample mean, but the distribution of the sample mean. That means if you take different samples of sample size n from this population, you'll end up with a k number of different samples. And then you'll end up with k number of different sample means. That's what we discussed last week. And the behavior of these sample means you can study it. That is called the distribution of the sample mean, or you can say the sampling distribution of sample mean X bar. Okay. Now this for the sampling distribution of sample mean, the mean and the variances are defined. Okay, when you are defining a distribution, you should be able to find the mean and the variance. Now in the case of sampling distribution of sample mean, the mean of that will be the mean of means. See, expected value of X bar, that is the mean of X bar, or you can say mean of sample means, or the average of sample means. Okay. Now, if your population, in the population that you take the sample, if that population has the population mean mu and the population variance sigma square, then the theorem is the mean of the sampling distribution of sample mean will exactly be the population mean. Okay, so that is a theorem. If you take a sample of size n from a population where the population mean is mu and the population variance is sigma square, the sampling distribution of the sample mean, it will have the mean value exactly the population mean, and its variance will be sigma square divided by n. That is the population variance divided by n. Okay, so this is the variance of X bar. Okay, so again, this is the mean of the sample mean. This is the variance of sample mean. Okay, so you have a distribution for sample mean, which is the sampling distribution of sample mean. That sampling distribution of sample mean has mean mu and the variance sigma square over n. Okay, so that is the theorem. Now, we have another important finding from this theorem. If the population from which the sample are taken is normally distributed. Okay, now if that population is normal, now you don't see any, you don't see whether the population is normal or any other distribution in this theorem 4.3. Okay, there's nothing mentioned about the distribution of the population. It only says the mean is mu and the variance is sigma square. But suppose that the population is normal. If the population where that sample was taken is normal with mean mu and variance sigma square, then the sample mean is also normally distributed with mean mu and variance sigma square over n. So that is one finding we derive from the theorem. If we know that the population is normal, then the sampling distribution of sample mean is also a normal distribution with the mean mu and the variance sigma square over n. So you can write When xi's are from the normal distribution mu and sigma square, this is from the population, then x bar will also follow the normal distribution, now with the mean, same population mean, and the variance will be sigma square over square root of n. That comes from the theorem 4.3. Okay. And then if you standardize it, what will happen? If you standardize x bar, that means you subtract the mean, divide by its standard deviation. What do you get? When you standardize, it should be the standard normal distribution. So that becomes a Z random variable. X bar minus mu over sigma square over n whole thing square root. You can write it as sigma over square root of n. And that will become a standard normal distribution. Okay. So those are two other extensions of this theorem 4.3. Okay. Now here's another one. If you have x1, x2 up to xn, IID normal random variables with mean mu and variance sigma square, then x bar, okay, that is the sample mean, and xi minus x bar, what is this? These are the deviations of each and every xi to x bar. They are independent for this I going from 1 to n. They are independent. What are the two quantities that are independent? X bar and xi minus x bar. That means x bar and these deviations from the mean to each and every number. Okay. Right. So that is another corollary that you can use sometimes in proofs. Okay, let's look at an example where we can use this sampling distribution of sample mean. In this example, you have two data sets. Both are of size 25. The first data set, now this y1, y2, these are not order statistics. Okay, this is a different section. Okay, so x1 up to x25, you have random variables of size, random sample of size 25. And another random sample of size 25, they are denoted as y1, y2 up to y25. There are two independent random samples from two normal populations. Two normal populations. The first one is mean 0, variance 16. Second one, mean 1, variance 9. So if I write it again, x will follow a normal distribution of 0 and 16. Y follows a normal distribution with 1 and 9. You have to find the probability that the mean of x's and mean of y's, x bar minus y bar, that is greater than 0. Okay. How are we going to find that? You already know that x bar, okay, if the populations are normally distributed, that is the corollary 431. If the populations are normally distributed, sample means are also normally distributed. So it is given that these are two independent random samples of normal population. So that means x bar is also normal, y bar is also normal. And what is the mean of x bar? Same as the population mean. Mean of y bar, it is again same as the population mean. What is the variance of x bar? Sigma over square root of n. Okay, so if x is n 0, 16, x bar is what? Again normal. Mean is the population mean, variance is 16 over the sample size, sigma square over n. And when y is n, y is normal with y mean 1 and the variance n, what is y bar? What is y bar? It is again normal. Mean is same as the population mean. Variance will be variance divided by the sample size 25. Okay. We want to find the probability of their difference. That is x bar 25 minus y bar 25. This 25 is there to indicate that the sample size is 25. Okay. And when you add or subtract normal distributions, it will be again normal. Okay, and remember this, if you subtract two normal densities, the means will be subtracted. That means you have 0 minus 1. Okay, the mean of x bar is 0, mean of y bar is 1. You subtract 0 minus 1, so your new mean will be negative 1. And when you do the variance, always you add. Whether you add or subtract, the variance you always add. So you have to add 16 over 25 and 9 over 25, which will be 25 over 25, 1. So the new variable x bar minus y bar will follow normal distribution with mean -1 and the variance 25 over 25, which is 1. Okay. You can do that with the normal distribution. Okay, only with the normal distribution, independent normal distribution. Okay, so can you see this? The means we subtract, variance we add. Now, if you add x bar and y bar, you add the means 0 and 1. Well, it doesn't matter, subtraction or addition, variance you always add. Remember that also, variance you always add. Okay, right, so that will be 1. So you find that x bar minus y bar follows the normal distribution with mean -1 and the variance 1. Okay, and what is our question? X bar minus y bar greater than 0, right? So if you want to find the probability x bar minus y bar greater than 0, you standardize it and read the standard normal table. So how do you standardize it? X bar minus y bar, you subtract the mean. Mean is -1 divided by the standard deviation. Variance is 1, standard deviation is also 1. So you end up with 1 over 1, which is 1. The probability z score greater than 1. So I have to read the z table. Okay. 1 will be somewhere here. You can find this probability. Okay, you know how to read the z table, right? You know how to read the z table, the standard normal table. So reading that table, you can find 0.1585. Do you want me to show how to read the z table again? Do you want me to show the z table and how to read this probability? Are you familiar with reading the table? Okay, then give me a minute. I'll open the z table for you and show you how to read it. Okay, I'm going to share the z table now. Okay, can you all see the z table? Can you see the z table? Can you see my shared screen? Okay, now tell me, how do you read this table? The standard normal table, symmetric about mean 0, always you read the left tail. Okay, always you read the left tail. So when you say z score 0.00, the first column, it gives you the z value up to the first decimal point. These are the second decimal points, 0, 0, 0, 1, 0, 2. The very first column, okay, the z values are the up to the first decimal point, then you have the second decimal points. Say, for example, if you want to read 1.95, how do you read it? You get 1.9 from the first column, and the second decimal 0.5 is from this one. So 1.95, it is this one. So this 0.97441 is what? For the z score, positive 1.95. Everything below this 1.5, this probability is 0.97441. Okay. Now, who can tell me what is the probability? Now, remember, always this table gives you the left tail. Always this table gives you the left tail. Tell me what is the probability of 2.53. Z-score 2.53. What is this probability? (2.53). How do you do that? 2.5, you find it from the first column. Okay, so I got some answers. Let's see. 2.5 is here. Next decimal point 3 is here. So where they cross? Here's the answer. So this probability is what? 0.99430. Okay. Right. So you know how to read it. Now what is this probability then? The right tail. How do you find this right tail? You do 1 minus 0.99430. Okay. Now tell me, how do you find the negative Z scores? You want to find negative, let's say 0.84. How do you find this 0.84? Negative 0.84. You don't have negative Z scores here. So how do you use the table? You have to use the symmetry, because if you read positive 0.84, this tail, they are the same. The right tail, left tail, this is due to the symmetry about the mean 0. So if you want 0.84, you read 0.84. Let's try it. Here's 0.84 is here. So 0.79955 is everything to the left. So this small part will be what? 1 minus 0.79955. And that is exactly same as this point. Okay, so from symmetry, you can find both negative and positive Z scores. So in our example, we had Z score greater than 1, right? We had the probability Z score greater than 1. So here's 1, here's 1.00. So this is the probability. That is the left tail. If you want the right tail, you do 1 minus 0.84134. And that is the answer. Okay. So this is how you get the result from the standard normal table. Okay. Is this clear to all of you? So I'll go back to our one. Okay, so 1 minus that 0.85 something, 1 minus 0.84134, that is 0.1585. So this is how you get the answer from the standard normal table. Okay. So all the now this example, it tests your knowledge about the theorem 4.3. You should know that the sampling distribution of sample mean has the mean, the population mean, and the variance sigma square over n. And from the corollary, you know that when the population is normal, the sampling distribution of sample mean is also normal. So you use that information to find the density of X bar and Y bar. And then the subtraction, again, that's from the independent normal distribution properties. You know how to find the new mean and the new variance of X bar minus Y bar. And then you standardize, read the Z table and find the answer. Okay. Right. So here's the sampling distribution of sample proportion. The sampling distribution of sample proportion, the mean of the sample proportion will be the proportion of the population, and the variance will be the proportion times 1 minus p. Q is 1 minus p. That is the probability of the failure. Okay, so when you say p is the probability of success, this is the success probability. Q is the failure probability. So in categories of, so if you think about the probability of success, the remaining will be the probability of failure. Since the total probability is 1, Q is same as 1 minus P. Okay. So if you have the population is finite and binomially distributed, okay, with P and Q, they are the respective probabilities of success and failure. And then you consider all possible samples of size n drawn from this population, you can find the probability, or you can find the sampling distribution of sample proportion. Okay, so that sampling distribution of sample proportion will contain the mean, same as the population proportion, and the variance P times 1 minus P over N. Okay. So we are not going to derive anything or do any examples with that, just these are for your knowledge. You will use them in categorical data analysis in a later course. Okay. And the next thing we have to discuss is about the sampling distribution of sample variance. Okay, so you have sampling distribution of sample mean, sampling distribution of sample proportion, and the sampling distribution of sample variance. Now, before we talked about the sample variance, you should know these three common distributions: chi-squared, student's t distribution, and F distribution. Okay. In this course, what we have to do is just to introduce these three distributions and their properties. But in 203 and later subjects, you will actually use them. Okay, especially in chi-square distribution will be used in categorical data analysis. Student T and F distribution, you will use them in regression analysis, time series, and also in the design of experiment, and also in ST203. Okay, so this you will learn about we will learn in detail about these distributions on the other courses. So we are going to introduce them in this course. Okay. So let's look at these distributions one by one. Chi-square distribution. Okay, the notation is the chi. This is the Greek letter chi. So we use the notation chi-square. Okay, so this is the chi-square notation. Right. So let's look at the chi-square distribution first. Now you can see the picture. The chi-square distribution is not symmetric like the normal distribution. Okay, so you are very familiar with the normal distribution, that nice symmetric bell. But when it comes to chi-square distribution, it is not going to be symmetric. You can see that it is a positively skewed distribution. Okay, the parameter that defines its shape and location, it is the degrees of freedom only. It's called the degrees of freedom. Depending on the degrees of freedom, the shape of the distribution will be different. As you can see, when degrees of freedom is 9, 5, and 1, how it looks like, right? So a chi-square distribution is a skewed bell like this. Okay. So therefore, the right tails and the left tails, okay, they will not have the same, probability for plus or minus values. It is not symmetric. Okay. Now, I think I mentioned you once about the chi-square distribution, how you get it. If you have x1 up to xn are independent normal random variables, so your x1 up to xn are independent normal. If you square it, okay, independent normal distributions, it means zero and standard deviation 1 unity. So that means your xi's are normal with 0, mean, and variance 1. That means xi's are standard normal. Then when you square it, you will end up with chi-square distribution with degrees of freedom 1. Okay, again, if your x is normal with 0, 1, that means standard normal. When you square it, it becomes chi-square density with degrees of freedom 1. And if you add these all xi squares, x1 square plus x2 square up to xn square, okay, that will be chi-square with degrees of freedom n. Okay, chi-square with n degrees of freedom. So that means the sum of xi squares will be chi-square with degrees of freedom n. Each and every x square will be chi-square degrees of freedom 1. When you add them, the sum will be chi-square with degrees of freedom n. Okay. So you can see this is how the chi-square distribution is formulated, right? And here's a part of the chi-square table. Now, usually in exams, you will receive a statistical table book. Okay, since you haven't sat for any exams yet, you don't know that, but in our department, we provide you a booklet that contains all the distributions: the binomial, Poisson, normal distribution, chi-square, TF, and all these distribution tables are there in that book. Okay, so you will see this type of one page for chi-square distribution. So I'll show you how to read it. Okay, but we are not going to do any calculations or anything. Just get familiar with this table and how to read it. You will use it later in other courses. Okay. Now in this chi-square table, you always get this right tail. Okay, and this is not like on the normal density. In standard normal table, you always get the left tail. Okay, from the table, the probability the left tail. But here, you don't get you don't get the probability for each and every chi-square value, but only for some defined probabilities. Okay, so what you see in these columns are, this is for different degrees of freedoms, the chi-square value when the right tail probability is 0.1. Okay, so this alpha means the probability. Okay, so this the subscript that you see 0.1 is the alpha. When alpha is 0.05, that means the tail probability is 0.05. When the tail probability is 0.05, what will be the chi-square value for each degrees of freedom? You can find it from the table. Okay. Now in this example, 3.841 is in your chi-square probability. If the tail probability is 0.05, this chi-square value is 3.841 at degrees of freedom 1. Okay. If I try another example, tell me this one. If my right tail probability is 0.025 with degrees of freedom 3, what is this chi-square value? Degrees of freedom 3, yes, degrees of freedom at the very last column. So you have to read this column, this row 3. At right tail probability 0.05. So here's 0.05. So what is that chi-square value? 9.3484. Okay. And and in most of the tables, you'll see the up to point, okay, next one. Say, for example, if you want to find this area is 0.025, then this will be 0.975. So these values are also available in this table. This is only a part of the table. Okay, so you'll see another column with chi-square 0.975, okay, somewhere to the left, right? So that will give you this number. Okay, this is only a part of the table, but you will see some selected, tail probabilities, to the left of this table. This is only a part of it. Okay, so there is a column for 0.975. That means the left tail 0.025, right tail 0.975. There's a column for that. And there's a column for 0.90, 0.95, and so on. Okay, so you can easily read the table. Okay. So chi-square distribution is usually used with the categorical data analysis. Okay. And the next distribution is the student T distribution. This is very similar to the normal distribution, but it has thick tails. Okay, approximately the normal distribution. Okay, it has nice bell shape, symmetric about the mean, very similar to the normal distribution, but the T distribution has thicker tails compared to the normal distribution. So you can see that. You can see the standard normal curve, the green one. You can see after Z score -3 and +3, the curve flattens. That means the probabilities are very, very small, okay, toward the tails. That means very thin tails for normal distribution. But the T distribution has thick tails. See, you can see, depending on, again, the degrees of freedom, see, you'll end up with thick curves like this. So normal distribution, it will be like this. Normal distribution, when it goes to infinity, the tail probabilities are approximately 0. Okay, this is Z. But the T distribution, it's not like that. You have thick tails. So that is the difference between normal and the T distribution. Okay, so T distribution is usually used with smaller sample sizes, right? Smaller sample sizes. So when you find probabilities with the normal distribution, again, you will learn this in ST203 when you do hypothesis testing. When the sample sizes are small, you can't use the normal distribution. You use the T distribution. Okay. When you construct confidence intervals and hypothesis testing, you will use the Z distribution and T distribution depending on the size of the sample. Okay, so just know that the properties of the T distribution. Okay, so here are the properties. It's symmetric about 0. When the degrees of freedoms becomes larger, it will approximate to the normal distribution. Okay, and here's a part of the T table. This is only a part. You can see the degrees of freedom 1, 2, 3 up to 27, and it goes down. Okay, this is only the upper part of the table. And again, you can see one tail and two tail probabilities, and they are T scores. So these are called T scores. Like Z scores, now in the T table, you have T scores. Okay, with the chi-square table, you have chi-square score, chi-score. Okay, so likewise. Now, how do you read this T table, right? So I'll show you one or two examples. So here's the T table, symmetric about the mean. Okay. If I want to find this right tail probability, 0.05, how do you find it? One tail. So you look at the one tail, 0.05, here's it, 0.05. For degrees of freedom, let's say 10. Degrees of freedom 10, see from the degrees of freedom, very first column, you find the degrees of freedom. So you go along that column up until you come under one tail probability 0.05. So what is the T score? 1.812. Okay. This is symmetric, therefore you can get the negatives also. So now suppose my left tail is 0.025. Only the left tail. So one tail 0.025. Here is it. Let's say now the degrees of freedom 15. So what is this T value? This T score, degrees of freedom 15, 0.025, it is 2.131. Now it should be negative. Why? Because it's the left side, 2.131. That is from the symmetry. Okay. You can't do this with the chi-square. Chi-square is not symmetric. Okay. Only T and Z you can do that. Okay. So 15 is degrees of freedom 15, left tail probability 0.025 is negative 2.131. Now what is this two tails? These two tails is, where should I write? Okay, I'll write this. Now suppose you want to find, here's my T distribution. I want to find the T scores where it should be symmetric. Okay, this is 0.025, this is 0.025. Okay, so both tails are what? Both tails contains 0.05. If you add 0.025 and 0.025, the addition is 0.05. Two tails is 0.05, one tail is 0.025. So that is why you see two tails is 0.05. Why? That is the twice of this addition, right? So it doesn't matter whether you read two tails 0.05 or one tail 0.025. It is 2.131. This is negative 2.131. This is positive 2.131. This is for degrees of freedom 50. Okay, shall we try another one? Can you find this one? Degrees of freedom, let's say 20. I want each tail to be 0.01. It's in there. Each tail is 0.01. Can you find this T value? Plus or minus? So when you find the value, please let me know. Degrees of freedom 20. each tail 0.01. Can you find it? Yes, degrees of freedom 20. One tail 0.01, so both tails 0.02. Okay. So here's the column. What is the value? 2.528. Okay, 2.528. So this is negative 2.528, positive 2.528. Now in the Z table, you have the probabilities for each and every Z score, but it is not possible in T table. For only selected tail values, tail probabilities, you can find the T value. Okay, so you can see the difference between T table and the Z table. You have this degrees of freedom associating with the sample size. And you can't find all the probabilities for all T scores, but only the T scores for some selected probabilities. Okay, right. So that is the T distribution. And the last one is the F distribution. The F distribution that was derived using two chi-square densities. You have two independent chi-square distribution, one with n degrees of freedom, the other one with d degrees of freedom. So n and d denotes the numerator and the denominator. And when you divide these two, okay, with their corresponding degrees of freedom, you'll end up with the F distribution. Okay, when a chi-square distribution of degrees of freedom n divided by the chi-square distribution of degrees of freedom d, and dividing their corresponding degrees of freedom, you'll end up with the F distribution with 2 degrees of freedoms n and d. So the F distribution has 2 degrees of freedoms. They are called the numerator degrees of freedom and the denominator degrees of freedom. Sometimes you use m and n. Okay, m for numerator, n for the denominator, first and the second. Okay, the F distribution is also a skewed one, like the chi-square density. Okay, and you can see some properties of the F distribution. Okay, you can read these properties leisurely later. Okay, and here's the F table. Again, this is only a part of the table, and in the booklet you get from the university, it will have different F tables for different these probabilities, the tail probabilities. Now in this table, all the probabilities are in the same, same table. But you will see different pages. For probability 0.1, you have one table. For 0.5, another page, and likewise. Okay. But anyway, you have the degrees of freedom in the numerator as the columns, and as the rows, you have degrees of freedom in the denominator. Right? C1, 2, 3, 4, and it goes on. Okay, this is only again a part of the table. Okay. Now, say for example, if I want to find the F value, here's my F distribution. Okay, let's say of the right tail probability. Okay, I want this right tail probability 0.05. Okay, F of 7 and 5. Okay, that means the numerator degrees of freedom 7, denominator degrees of freedom 5. So numerator degrees of freedom 7 is here, 5 is here, tail probability 0.05 is here. Can you see that? So I use this line. And what is the F score? 4.88. 4.88 F score, the right tail probability is 0.05. So this is how you read the F table. Okay, let's try another one. Tell me this one. The right tail probability is 0.025. I need the numerator degrees of freedom 3, denominator degrees of freedom 4. How do you find it? Numerator degrees of freedom 3 is here, third column. 4 is the denominator degrees of freedom, and I want tail probability 0.025. Okay, so I go along this line until I come under 3. So here's it. 9.98 is the F score. Okay. So likewise, you can find the F scores. And there are few more properties of the F distribution. Okay, if you have the F score for Fmn for a certain probability, then if you take 1 minus that F score, that will be F of Nm. That means you strip the numerator degrees of freedom and the denominator degrees of freedom. Okay. So if your F score is, say, F for Mn degrees of freedom, when you take its reciprocal, you just change N and N. Okay. So that you can try later with your, this table. Okay. That is one nice property about the F distribution. So you will use this table a lot in future courses. Okay, in this course we are only introducing it. Now, have you ever wondered why it is called the F distribution and why this is called the T distribution? Right? Chi-square is okay. It's a letter in the the Greek alphabet, but T and F. Why do you think that they are T and F? Any guess? Anybody who knows why? What is the reason for F? Anybody? Do you know what this F stands for? Because this distribution was developed by Ronald A. Fisher, so F is for Fisher. So who's Fisher? Anybody who are familiar with this name? Who's Ronald Fisher? You should know him. He's the father of the modern statistics. Fisher is the father of modern statistics. Sir Fisher, he was knighted by the Queen of England for his service to the academy. Father of the modern statistics. Many, okay, you will learn a lot of things developed by Fisher in ST203, the Fisher score, F score, and there are a lot of theorems that was developed by Fisher in categorical data analysis, in design of experiments, in hypothesis testing. You will see a lot of theorems and things developed by Sir Fisher. Okay, so F distribution it's named after Sir Ronald A. Fisher, who's the father of the modern statistics. Okay, and the T distribution, and it's called the student T distribution. Okay, why it's called the student T distribution? I don't know whether I shared this story with you in previous course. I guess not. Anybody who knows why it is called students T? I don't think I shared this story with you. Okay, it's about, again, it's the person who developed this one. The T distribution was developed by not a statistician, actually, it's William Gossett. Okay, William Gossett is the person who developed T distribution. This person is a genius. He had 2 PhDs by age of 26. Okay, can you imagine that? At age of 26, he had 2 PhDs, one in chemistry, the other one is in mathematics. Now my chances are gone. So if you can try, you can beat him. Okay, chemistry and mathematics, 2 PhDs by age 26. Okay, and from, I think it's from Oxford or Cambridge. Okay, very, very renowned universities. He got 2 PhDs by 26. He's a genius. Now this William Gossett was the chemist in a certain brewing company, which is called the Guinness Brewers. Brewing companies where you make beer and wine, stuff like that. So in this brewing company, William Gossett was the chief chemist. He was doing experiments with the beer samples, wine samples, and so on. But in these experiments, he was given only, the sample sizes are very small. You will get, small shots of maybe only 3 glasses of wine for a certain test, only 5 glasses of beer for a test. So he has only 5, your sample size is 5, 3, 6. So he found that when he's developing or doing this statistical analysis, the normal distribution was there at that time. He found that the normal distribution fails. The results that you get from using the normal distribution, the probabilities, they are wrong because the sample sizes are small. Normal distribution is you can use it when the sample size is greater than 30. Okay? The normal distribution will work very well if the sample sizes are large, 30 or more. Now, if you have smaller sample sizes, the normal distribution fails. Therefore, William Gossett developed this T distribution. He just gave the name T. And then, although he wanted to publish it, the Guinness brewers, they have this rule, you can't publish your work. The workers in that company, they can't publish their work because they are like business secret. So they were not allowed to publish their findings. So William Gossett wanted to publish this very badly because, this distribution is very useful. Okay, people can use it. So he went to his supervisor. His supervisor is the Carl Pearson. You know Pearson, right? You know Carl Pearson, who's the Pearson's coefficient, the one who developed Pearson's correlation coefficient. So Carl Pearson was his supervisor, and Carl Pearson has the journal Biometrica, the Biometrical Journal, the well-known Biometrical Journal was done by Carl Pearson. He's the chief editor. So Gossett went to his supervisor and showed this nice finding. So he said, okay, we'll publish it, but he can't use the name. It's violating the rules of their brewing company. So he used the name student because he's the student of the editor, Pearson, right? So he published his work under the anonymous name student. Therefore, it was known as the student's distribution. No one knew until his death that William Gossett is the student, right? So anyway, this is still now we are using that student T name for this distribution, which was developed by William Gossett. Okay, so that's how you got the name T and F. Okay. We have to do a few more stuff. Okay, this is another theorem. About the Chi-Square densities. Okay, so you can look at this. When you have IID normal random variables of size n with mean mu and variance sigma square, then the sample mean and the sample variances are independent. And if you divide n minus 1 s square, that is n minus 1 times the sample variance divided by the population variance. Okay, and that will give you the chi-square degrees of freedom n minus 1. Okay, so that is one more theorem, and then you can get the sampling distribution of the sample variance. When you have x1 up to xn IID normal variables of size n with mean mu and variance sigma square, the expected value of the sample variance is the population variance sigma square. The variance of the sample variance is given by this expression 2 sigma square n minus 1. Okay, so these are just the information about the sampling distributions. No need to memorize them. Okay, but these are for your knowledge. So in this course, we have to introduce these things to you. Okay, but you will be using them in details in later courses. And here's how you develop the T density, T distribution. Okay, so when you have xi is the normal distributed with sample size n, again the normal with mean mu and the variance sigma square. If x bar and s square are the sample mean and the sample variance, then if you do x bar minus mu over s over square root of n, not sigma, but s over square root of n, that will follow the T distribution with degrees of freedom n minus 1. Okay, so you will use these values when you develop confidence intervals in ST203. Okay, so just know that you have seen this in this course, that's enough. We are not going to use any examples or calculations in this course, but we are just introducing, but you will use them in future courses. Okay. Right. So that's the end of chapter 4. Okay. I have already uploaded a tutorial covering chapter 4, so please try it. Right. Chapter 5, both online or the both video sessions will be there tonight. First one is already there. Second one I will upload tonight. So that will be chapter 5. And later we'll do a discussion for covering a few examples from chapter 5, after the exams are scheduled. Okay. Any questions so far? Okay, then let's stop for today. So I will upload the video and the notes. Please go over them leisurely, especially the theorems that we discussed at the end. Okay, you don't have to memorize them, or you don't have to memorize these equations or anything, these theorems, but just be familiar with the words and their properties. That's enough. Okay. Right. We are not asking any questions from these in exams, but just for your knowledge. Right. Order statistics that you have to understand very thoroughly.